Okay, we'll continue developing the theory required to look at the resultant of two perpendicular vectors. The point O will be reserved now to mean the origin. That is, we're not really allowed to use the point O to represent a point unless that point is the special point, the origin, or in other words, the reference point, typically the center of the diagram. Not always though, the center. The vector OX can be written shortly as X. In other words, if it looks like we're missing a point to define our vector as joining two points, the absent point is actually the point O. You can think of this somewhat similar in algebra. 1x is the same thing as x, so in vectors, OX is the same thing as x. It's not that there's something missing in front, it's just that something is the point O, and for convenience and elegance that is left out. These vectors that start at the origin are called position vectors. So OX is an example of a position vector, and it can be written as X. On this diagram here, you can see the origin O in the bottom left and the 3 points A, B, and C. You can see the vector OA represented by A, OB represented there by B, and OC represented by C. So these are three position vectors, all starting at the origin. That's really the key thing about position vectors. Let's develop a rule now which will actually be very useful and very simple. AB is equal to AO plus OB. This is our basic rule that we have from adding vectors when we're dealing with points. Now, OB is just a position vector, so it can be written quite shortly as just B. And then AO can be written as minus OA. Again, this is one of our two basic rules that we saw earlier. Now, OA is a position vector, so it can be just written as A. And clean this order up a little bit, we can now say AB equals B minus A. So we have a very simple, but actually very useful and powerful rule. The vector AB is not a position vector. It's a vector that joins AB. But the vector AB can be written as two position vectors, vector B minus vector A. So in other words, AB can be changed into a position vector. Let's have a look at an example. Express the red vector DB in terms of the position vectors AC and E. The distance between ED is twice DC, and B is the midpoint of AC. So we're looking for DB, that red vector. So DB is equal to B minus D. That's our new rule that we developed. B is equal to A plus AB. And likewise D will equal E plus ED. And if you have trouble seeing that, just picture the A and E as OA and OE. Now, since AB, or B, is the midpoint of AC, we can say AB is a half AC. And likewise, we can say ED is 2/3 EC. Drop in the brackets. We have A plus a half AC minus E minus 2/3 EC. AC, using our rule again, is C minus A. And EC, again using our rule, is C minus E. Multiplying through, I get a half A plus a half C minus a half A, and then minus E minus 2/3 C plus 2/3 E. So we want to group terms together. A minus a half A will be a half A, then a half C minus 2/3 C will be minus 1/6 C, and then we have minus E plus 2/3 E, that will be minus 1/3 E. So we've now written the vector DB in terms of the position vectors AC and E. dB is a half A, negative sixth of C, and negative third of E. And just to finish, I want to introduce some notation. The length of vector x, or the magnitude of vector x, is denoted by these vertical lines around vector x. So if you put these lines around x, it means it's the length of x. And likewise, you can represent the direction of vector x by putting this angle symbol in front of the x.